We will now introduce some terminology that will allow us to assess the steady-state error of a system at a glance, as opposed to having to necessarily apply the final value theorem. So in the previous example, we saw that adding integral control enabled our plant to track a step input with zero steady-state error. And this trend or effect is true in general. The presence of pure integrators, poles at the origin, tend to reduce the steady-state error to all types of inputs, steps, ramps, etc. The number of integrators is identified by something called a system's type. So more specifically, this is the definition of system type. The number of poles at the origin in the forward path of a unity feedback control system is called the system's type. So in particular, it must be a unity feedback system that has this sort of structure. And it doesn't matter if these poles are in the controller or the plant. So it doesn't matter if we added the integrator with a PI controller or if the plant itself already had an integrator in it. But for the above structure, where we have the product of the controller and the plant, this is an example transfer function where it has s to the n power in the denominator. In other words, it has n poles at the origin with value equal to 0. So we define this to be a type n system. Let's look at a few examples. So let's say we have a transfer function of that form. So looking at this, it has a pole at -4, but it has no poles at the origin. It has no poles s equal to 0. It has no integrators. So we define this to be a type 0 system. Let's look at another example. So in this case, we have a single pole at the origin, or a single integrator. It has this form where n is 1. So it has s to the 1 power. So we define this to be a type 1 system. And if we go one step further, here we have 2 poles at the origin. Here n is equal to 2. And so this is called a type 2 system, under the conditions that it's in a unity feedback structure such as this. So in the first example we did in this module, we didn't, strictly speaking, have a unity feedback system because we had some dynamics in the feedback path, but it ended up that this term didn't affect the final value because it had a DC gain equal to 1. So let's hypothetically say we had the same system but with a 1 replacing it. That system is a type 0 system because it didn't have any integrators in the controller or the plant. And we saw that when we solved for the steady-state error, that it was non-zero. It was some non-zero value. We then added an integrator to the controller in the second part of the example, such that the system became a type 1 system. Again, if we had a 1 in the unity feedback path, and we saw that it was able to track a step with 0 steady-state error. It turns out it would not be able to track a ramp with 0 steady-state error, however. But if we added a second integrator, so it said it was a type 2 system, then it would be able to track a ramp. So this can track a step with 0 steady-state error. And this can track a ramp with 0 steady-state error. One way to try and remember this is is the fact that what we're observing here is a special case of something called the internal model principle. What the internal model principle in essence says is, if we have a unity feedback system like this, where the forward path includes a copy of the reference, then the system can track that reference with zero steady state error. So in this case, a type 1 system in essence has a copy of a step in it, and a type 2 system in essence has a copy of a ramp in it. So since a type 1 system includes a copy of a step, it can track a step with zero steady state error. And since a type 2 system has a copy of a ramp in it, it can track a ramp with zero steady state error. Okay. On the next slide we have a table summarizing some of these facts. So considering the structure that we had on the previous slide of a unity feedback system, this table summarizes what the steady state error is for different types, for different system types, type 0, type 1, and type 2, and for different types of inputs, a step input, a ramp input, and then in essence a parabolic type input. So we recall from our earlier discussion that a type 0 system cannot track a step input with zero steady state error. It tracks it with some non-zero error. So we end up with a picture like this with some steady state error. If we add an integrator to the system, then we have a copy of a step input in our forward path, and according to the internal model principle, that means that we can track that input with zero steady state error. So now the steady state value of the response approaches the commanded reference, the step reference. If we have a type 2 system, a type 2 system has two integrators in it. So in essence, it also has a copy of a step input. It has, in fact, two copies of the step. So it too can track a step input with zero steady state error. If we go to a faster changing input like a ramp, then a type 0 system can't track a ramp input at all. So if we have a ramp reference, the type 0 system will also grow to infinity, but it'll grow to infinity at a different rate. And so as time goes on, the error, the difference between the commanded reference and the actual output, will grow and grow and grow. A type 1 system doesn't have an exact copy of the ramp, so it too cannot track the ramp perfectly, but it at least has a finite error. So in this case, if the reference is a ramp, the type 1 system won't exactly equal the reference, but it'll grow at the same rate eventually, such that the error reaches some finite non-zero value. A type 2 system, however, does have a copy of a ramp built into it. If you recall, a ramp, the Laplace transform of a ramp is 1 over s squared. And so it will be able to track a ramp with zero steady state error. An acceleration input, its Laplace transform continues this trend. It's 1 over s cubed. And so the type 0 system, the error will go to infinity. A type 1 system, the error will go to infinity. But the type 2 system can track it with some amount of finite error. And this trend continues. In essence, the faster the input is changing, the larger the error will be, the harder it is to track. So going even further, while keeping the unity feedback structure of the previous slide, but then rearranging our forward path into this form where we factored out a constant k such that the constant term in the polynomial of the numerator and the constant term in the polynomial of the denominator is equal to 1, then we can go even further and redraw the table from the previous slide, but instead of just simply saying that the error is non-zero for a type 0 system tracking a step, or a type 1 system tracking a ramp, or a type 2 system tracking a acceleration input, we can more specifically define how large that steady state error is in terms of the gain k. This case of a type 0 system tracking a step, we saw that the steady state error in the very first example had a form like this, where it was a constant divided by a constant plus k. This k is also called the static position error constant. Similarly, if we took a type 1 system like the second example, but instead of feeding it a step we fed it a ramp, we would see that the steady state error had this form, where in that case the k is given a special name of the static velocity error constant, and for an acceleration input it's called the static acceleration error constant. And so this table and the one preceding it in essence give us a shortcut for determining the steady state error of a system. This is a handy thing if you, for example, have the standard form of a unity feedback system and you rearrange the forward path to have this structure. It's a very simple way to estimate the steady state error without having to explicitly find an expression for E of s, without explicitly needing to take the limit as s goes to 0. But if you don't have this special structure, you can always fall back to the final value theorem. If you have something in the feedback path, if you're trying to determine the steady state error in response to an input that enters in a different location than the reference, for example, if you're trying to find the steady state error due to a disturbance or due to noise, then you can't necessarily use this table, but you can still employ the final value theorem. So this brings us to the conclusion of Module 16. In this module, we demonstrated how steady state error can be calculated employing the final value theorem. We also demonstrated how adding integrators to either the controller or the plant tends to help reduce steady state error. And finally, we introduced the definition of system type, which can be used as a shortcut for determining steady state error, but can only be used if the system has the specific structure defined. That is, if it's a unity feedback system.